But this talk is really a lot of application, as Jim sort of already mentioned, less about sort of mechanics and models. You guys already know that. You've learned that the last week and a half, so I get to talk to you about, now that you know the basics, here's what we can do with some of it. And as I go along, this is, stop, ask me questions, let's have a conversation. It's really boring if I talk at you for an hour. I mean, I can do it, but please don't make me. Okay, so when we're thinking about food and sort of the way I'm going to divide this talk, I'm going to think about three sort of categories of food items. Animal-based foods, so things that come from animals, so your meats, your eggs, dairy products. Plant-based food items, we'll talk a little bit about that. And then beverages, which I think there's a group in IsoCamp working on Coca-Cola. Is that right? Yes? Yeah, okay. So we can think about sort of what we could term natural beverages, bottled waters, milk, juices, or manufactured things that we actually make, beer, wine, and soda, and I'll show you some examples of that. But before we get into talking about sort of these applications and what we do with stable isotopes, I want to pause and talk a little bit about sampling, because you guys have been talking about that, I'm assuming, in lab. Yes? What makes a good sample, how you get a sample, why you might want to sample. So, you already know why we sample. We can't measure the entire population, so we need to collect a sample and then make an inference about the larger population, however we define that. So, if you're going to do this, if you're going to sample and then make a measurement and apply it to a population, you better make sure that your sample matches your population. So this is the first time I've done this, but it's a sampling example. So here, you guys have all sampled M&Ms, okay? So go ahead and open them up. And this is the production of M&Ms. This is some historic data from 2008, but they don't, what was this? They don't actually create or make even numbers of M&Ms. So how did our samples, how did your samples match this worldwide population of all M&Ms out there? So I'm curious to see if anyone hits this even closely. Okay, so according to this, you guys should have more blue than anything else. Yes? No? All right, so we've already sort of skewed our sample here. Yes? Okay, so we have some, but not others. Now, if we were to combine all of our counts, which we won't take the whole class period to do that, we may actually get closer and closer to this sort of ideal, right? But this is what you need to think about when you're sampling. What's the population you're trying to estimate? How well does your sample represent that? Sometimes you can't know it, but you can make some pretty good guesses. And the more you sample, hopefully the closer you're getting to the real population. Okay? All right, now you can eat them and we can keep going and talking about food. It was really just a way to get you guys to have some candy after your dinner there. So now you can have a sugar rush and hopefully stay awake. Okay, so this is the example that we talk about, and this is less exciting. I could have given you a whole bunch of raw shrimp and we could have sampled those, but that didn't seem quite as appealing. So we have two populations here of shrimp. One that they all sort of look like the same color, and the second population where we have three different colors. So how do we select a representative sample? Well, in population A, it doesn't really matter if any four that you select out of that, if you take half of that population and analyze it, it's the same. In population B, if I'm going to collect 4 shrimp, there's actually 70 different ways to do it, and only 24 of those are really going to be representative of the population at large. So thinking about sampling and how we do it is really important in food, and I'm talking about food here, but of course in any of these applications. So, some considerations when you're thinking about sampling. Is your sample homogeneous to the smallest size that you're going to analyze, right? So you guys have been sitting up there and weighing tiny little samples or pipetting tiny little water samples. Is your sample homogeneous at that level, at that small scale? If it's not, how do you make it homogeneous? You can isolate a specific component so you can get rid of sort of noise or interference, or you can try and homogenize everything, grind it to a fine powder. So here's an example of how we sampled. This is a royal we. I actually didn't do any of this. Scallops. So the initial questions here, when we're looking at sampling these scallops for isotope analysis, we have 1 kilogram. This is with their shells on, of course. 24 individuals. They all look about the same size. They all have about the same shape and color. Very similar pattern. So how are we going to make a representative sample for our isotope analysis? We're going to take that 1 kilo and we're going to take it down to a 0.5 milligram sample, which is about, well, you can see the percentage, 0.5 ppm of our original mass. So we really need to be thinking carefully as we take, here's my bulk sample, and get it down to the size that I actually need to analyze. So, of course, we could take the whole kilo of scallops and we could dump it in a blender and go to town. But when you eat a scallop, what are you eating? You're not eating the shell. So that's pretty quick and easy to say, let's get rid of those. So we open them up, and here they're kind of manky on the inside, but we're going to go after that muscle there, which is what most people think of when they get the pretty scallops in the restaurant. So here they are. They've been removed. It's about 165 grams. They're nice and juicy and wet, so there's a lot of water in here, of course. So we shove them into a blender, and we coarsely chop them, and we make scallop puree, basically. I know, delicious. I heard some oohs, but isn't that tasty? And here it is. We've now taken that, and we flattened it into a plastic bag. It's about 100 grams in each plastic bag. We smash it into this thin layer. We're going to pop it into a freezer, have a little slit in the bag. We're going to freeze it completely solid. Then we're going to take that, and we're going to pop it into a drying oven or a freeze dryer, whatever we have at hand. Freeze dry it here until we have now made scallop jerky, basically. And we've taken our 1 kilo sample, and we're down to about 20 grams. So we've dropped a lot of mass here. But it's still sort of all nice and representative because we chopped it all up in our blender in the beginning. Now we're actually going to take that jerky, that scallop dried mass, and we're going to remove the fats from it, just using a quick couple of hour reflux with hexane in this case. Why might we want to remove the fats? Yeah? Yes, they do. They're very distinctive. So lipids have a very distinct, they typically are isotopically much lighter, have lower isotope ratios than the meat or protein portion. And if you have a sample that has more or less fat, you're going to have a different contribution from that lipid signal. Yeah?
Do you always use hexane as a solvent?
No, just in this example. This is actually a collaborator of mine who took all these great photos. When I was doing my thesis work and was working with hamburgers, I used chloroform, methanol. Sometimes if I had rubbing alcohol and I was on the road, I would deliquefy with rubbing alcohol. And yeah, that was kind of gross, but you just need to get the fat out.
Hexane is also appropriate solvent to extract lipids.
Mm-hmm. If you want to actually keep the lipids. So what I did for my thesis work is I would just do big batches and I would not actually collect the lipids, I would just toss those, but you could actually individually extract each sample and analyze the lipid component as well. I just chose not to do it in some of my work. Okay, so here it is. They've now been delipified here, and we have even lighter, fluffier scallop jerky. We're down to about 5 grams. Some of the final steps here, we take this and put it into a ball mill, grind it to a really fine powder. This is a metal-free ball mill because we actually analyzed these for element concentration as well, so we didn't want to introduce a whole bunch of elements that weren't already there. And then take it through a fine sieve to remove any sort of final connective tissues or anything that didn't grind up into a nice powder. Here it is, and there's our final sample of powdered scallop meat in a sterile container. We have about 3 grams from that 1 kilo that we started with. From there, we can weigh out our 0.5 milligram sample if we're measuring carbon and nitrogen, if we're interested in hydrogen and oxygen, or sulfur, or strontium. The sky's the limit at that point. So here we are, we're going to weigh it into our 10 capsules. You guys have done this, and pop it onto the instrument. So that's how we sampled the scallops. Okay. Now I'm going to go talk about some applications since we talked about sampling. So if we think about the isotopes, I just mentioned a whole suite of them that we can analyze. We can sort of divide them into 2 groups about the types of information we're going to get from them. We can think about geoelements that kind of come from bedrock, soil, environment. So that's typically strontium and lead in my world when I think about isotopes. And then the bioelements, which is primarily what I work with and is what I'll be talking about primarily tonight. hydrogen, carbon, nitrogen, oxygen, and sulfur. And these are really, you guys have been learning what causes variations in these isotope ratios in plants and animals, right? That was the whole last week and a half, biological processes, environmental processes. So, we're going to go through this. I just want you to have this if you keep all of these notes together, but you probably know all of this already. Why do we get variation in carbon isotope ratios? A lot of it is linked to photosynthesis, where you have C3 plants with a distinctly different isotope ratio from C4 or CAM plants. Whatever an animal is eating is going to impact the isotopic composition of its tissues. So diet comes into play here, and we just talked about the fact that a bulk tissue is going to be a combination of all different components. So you want to think about the components that you're interested in analyzing. None of this is new, right? Good. Nitrogen. Ecosystem influxes, and so additions and losses are really what's really at play here. Fertilization, nitrogen deposition, and nitrogen fixation. You can get gaseous losses and leaching from hydrologic losses. In general, and this is a rule of thumb, as you go up in trophic levels, you get higher delta 15N values, but the type of protein you have in your diet and the quality of that protein really plays into this. And then again, if you are interested in different components, they might have different isotope ratios. Okay, hydrogen and oxygen, just a quick reminder. Water cycles, what's driving a lot of the variation. We know that we start with ocean water that has an isotopic composition of 0 by definition. Fractionation causes these global patterns. We've seen the isoscapes. You guys have seen this over and over again, this global meteoric water line. And plants and animals are going to record whatever they're drinking into their tissues with some fractionation effect. We could take that, predict back their drinking water. Yep. Good on all of this? Great. We're through the intro bit. Any questions so far? How are the M&Ms? Delicious, fabulous.